So we saw that just making up a way of multiplying vectors, it's sort of the obvious choice for what a product should be, doesn't actually work. It doesn't give you a geometrically meaningful result. So maybe to come up with a way of multiplying vectors, we should look for geometrically meaningful expressions that look like products. And here's one example of that. So if you take the magnitude of a vector, remember the magnitude of a vector is its geometric length, so the square root of v1 squared plus v2 squared plus v3 squared. So if you square the magnitude of a vector, well, that gets rid of this square root, and you just get v1 squared, which I've written as v1 times v1, plus v2 squared, that's v2 times v2, plus v3 times v3. And this kind of looks like we multiplied v by itself, right? So maybe what we should do is define a new product. We'll use a dot for this product just because, I mean, we have to use some symbol. So dot is how we will pronounce this product. So v dot w, and it will be, well, v1 times w1 plus v2 times w2 plus v3 times w3. And of course, this last term is just if we're in 3D. If we're only in 2D, then we'll only have the first two terms. And in fact, if you are in a larger dimensional space than three-dimensional, you might actually have other terms on the end here. So this is a perfectly fine way to define a product. The question, of course, is it geometrically meaningful in any way? If you rotate the coordinate system, all of these individual numbers will change. And the question that we will eventually have to answer is, even though the individual numbers are changing, does the overall quantity change or not? But before we do that, first of all, let's name this product. So this formula that we've invented, that we're going to use at least for now, is called the dot product. We use you do need to write this dot symbol. If you don't write the dot symbol, nobody's going to know what you mean, right? So, in particular, well, because we have more than one product, already we have a scalar product and this new thing which we're calling a dot product. So do write this dot symbol, and it's just given by this formula, right? So one advantage of the dot product is computing it is very straightforward. One disadvantage is that it's unclear at the moment if it means anything. But computing it is straightforward, right? So 23.45 is 2 times 3. This dot here, this is the scalar, I shouldn't say scalar, this is real multiplication. Okay, plus 4 times 5, so that's 6 plus 20, so 26, right? So this is dead easy to calculate. It's not clear if it means anything though, right? Remember, we did guess a formula for a product already and it failed, so we've guessed another formula, we've invented another formula. It's not clear if it will fail or not. To get a handle on if this means anything or not, we need to dig into some algebraic properties of this product. So first of all is its relationship with magnitude. The square of the magnitude is v dot v. So that's clear from the formula, right? V dot v is v1 v1 plus v2 v2. And if you're in 3 dimensions, plus v3 v3. But yes, that is actually just the square of the magnitude of v. The second thing to observe about this product is that it's commutative. V dot w is equal to w dot v, right? This you can work out just from writing out both sides. So on the left-hand side of this, right, if we work out v1, v2, v3 dot w1, w2, w3, what we get is v1, w1 plus v2, w2 plus v3, w3. But each of these products here is real multiplication, and real multiplication we know is commutative, so we can turn it around like this. Just put all the w's first. But that is exactly w dot v, right? So w dot v is v dot w, right? So this is a commutative product. That's nice. The final property that I want to point out about this product, I guess second to last, is that this product distributes. So if you have three vectors, u, v, and w, and you add two of them, and then dot with the third one, that dot product distributes over the sum, right? So this is a vector sum here. We can prove this, again, just by writing everything out in terms of coordinates. It's a nice little exercise. You should do it once in your life, but I won't write it out because you just write out everything in terms of coordinates, distribute your real multiplication, and then gather things back up into vectors. A similar product is that, or similar fact about our dot product is that it plays nice with scalars. So if you have a dot product of two vectors and afterwards you multiply by a scalar, you can put that scalar anywhere you want. You can put it outside the dot product, you can put it in the first factor, or you can put it in the second factor. What you don't want to do, though, is put it in both, right? Because this would actually be the square of your scalar times v dot w. And again, you can prove this just by writing everything out in terms of coordinates. So I'll let you work that out. All right, so this dot product, it has some algebraic properties, right? It distributes, it's commutative, and it has this nice relationship with magnitude. So let's come back to the geometry of the dot product. So we defined a dot product in terms of coordinates. We want to know if we changed our coordinate system by sort of reorienting it in space, would that change what the dot product gives us? So here are two vectors, v and w. Maybe I should put vector hats on these. Here are two vectors, v and w, and what we want to think of is what exactly is the dot product of these vectors. Okay. Well, I don't know about you, but when I see this kind of picture, my eye kind of tries to fill in this third side here. But if we're talking about vectors, then maybe we should make this a vector instead of just a line segment. So it's not clear which way we should make this vector point, upwards or downwards. It turns out it doesn't matter. Let's make it point this way. We should figure out what this vector is, though. This is some vector, temporarily let's call it u. This is some vector u so that w plus u is equal to v, right? Because if you start at this left-hand point and you follow the vector w and then you follow the vector u, you end up at the end point of v. So w plus u is equal to v. And that means that this third side, the vector u, is actually just v minus w, right? We can subtract w from both sides. Okay. So we have this triangle. What do we know about triangles? I mean, this triangle it might be a right triangle, but usually it won't be. The things we know about triangles in general are that their angles add up to a half turn, 180 degrees, or pi radians. We know the law of sines, and we know the law of cosines. In this diagram, I mean, since we're starting with v and w, it seems like this is the most important angle, the angle between v and w, so let's call that theta. And so we might write the law of cosines for this triangle. The law of cosines for this triangle says that, let's see, if we're going to use this angle theta in the law of cosines, then we need to start with the side u, and remember that's v minus w. So the law of cosine says the length of the side u, so the magnitude of v minus w, squared equals the top side squared, length of the top side squared, plus the length of the bottom side, that's magnitude of w squared, minus 2 times the magnitude of v times the magnitude of w times the cosine of the angle between them. Okay, but what does any of this have to do with the dot product? Well, remember, one of the things we noticed about the dot product is that it's related to the square magnitude of a vector. So any of these square magnitudes we could replace with the corresponding dot product. It takes a little experimentation to see which one is fruitful. Let's do it with them all, I guess, though. So on the left we have v minus w dot v minus w. And on the right we have v dot v plus w dot w minus, and then these magnitudes over here aren't squared, so let's leave them written as magnitudes like this. Minus 2 times magnitude v, magnitude w times cosine of the angle between them. Okay, well, this dot product here, remember the dot product distributes over vector addition, so we could actually multiply out all of these products. So this is going to be v dot v minus v dot w minus w dot v plus w dot w. Okay, and then on the right hand side we have the same stuff as before. V dot v plus w dot w minus 2 times magnitude of v times magnitude of w times cosine of theta. All right, well look, now some stuff starts canceling. That's promising. So this v dot v cancels that v dot v, this w dot w cancels that w dot w. And on the left hand side, v dot w and w dot v, those are the same because the dot product is commutative. So this is minus 2 times v dot w. So minus 2 times v dot w equals minus 2 times the magnitude of v times the magnitude of w times the cosine of the angle between them. But then we can cancel the minus 2's. So what we get is v dot w, I'm writing this big now, v dot w equals the magnitude of v times the magnitude of w times the cosine of theta. And remember, theta is the angle between v and w. So this is actually kind of a surprising result. We invented this dot product basically out of nothing, but it turns out that it actually gives us some geometric information. V dot w is the magnitude of v times the magnitude of w times the cosine of the angle between them. And maybe the most important thing about this formula is that this doesn't depend on the orientation of the coordinate system. Right? If we turn our coordinate system and write v and w in terms of different coordinate systems, well, that rotating the coordinate system won't change the length of v, won't change the length of w, and also will not change the angle between them, and so won't change the cosine of the angle between them. So this dot product doesn't depend on the coordinate system, which is kind of funny because the formula for the dot product looks like it should depend on the coordinate system because the coordinates of v and the coordinates of w show up. So this is the surprising thing about the dot product, and it's kind of the reason the dot product is important, really. So this is so important that I'm going to give this a name. I don't think everyone calls it this, but I call it this. I call this the geometric formula for the dot product, right? So this is a super key fact about the dot product. This is the reason why the dot product is important. So v dot w is equal to the magnitude of v times the magnitude of w times the cosine of the angle between them. All right. So this tells us why we might care to calculate the dot product, other than the fact that it's easy to calculate. So for example, what is the angle between these two vectors, 2, 1, 4, and minus 1, 6, minus 2? In the plane, if we had two vectors in the plane, finding the angle between them would be a matter of just a little trigonometry, but these vectors are in 3D space, and I think the problem of finding the angle between two vectors in 3D space it's a lot harder, right? I mean, there is some angle between them because these two vectors right? There's some plane that contains these two vectors, and you can measure the angle in that plane, but I mean, what is that plane, and how do you actually measure that angle? In general, it seems like a pretty tricky problem, but we know the geometric formula for the dot product. So we know that v dot w is equal to the magnitude of v times the magnitude of w times the cosine of the angle between them. V dot w, that's easy to calculate, and these magnitudes are also easy to calculate. So we can just solve for the angle theta. So v dot w, let's see, it's 2 times minus 1 plus 1 times 6 plus 4 times minus 2. The magnitude of v, that's going to be the square root of 2 squared plus 1 squared. Oh, that should be a squared. So 2 squared plus 1 squared plus 4 squared. The magnitude of w is going to be minus 1 squared plus 6 squared plus minus 2 squared. And then this angle theta, that's what we're trying to find, so we don't know what theta is yet. So now we can just do all the arithmetic. So let's see, minus 2 plus 6 minus 8, so that's going to be minus 4, I think, equals square root of, so let's see, 16 plus 4 is 20, 21 times, let's see, 36, 40, 41 times the cosine of theta. So the cosine of theta is going to be minus 4 divided by the square root of 21 times the square root of 41. And then we can just use inverse cosine or arc cosine. So theta is arc cosine of minus 4 over square root 21 times the square root of 41. And this is some angle, right? I'll let you dump this into a calculator. So one thing we can do with the dot product is calculate angles that would be very difficult to calculate otherwise, right? Let's think about, this geometric formula for the dot product, right? I guess notice this, that this dot product here, in this example, it came out to be negative. And so we might look at the formula for the geometric formula for the dot product and ask ourselves, why would this be negative? Okay. In other words, let's think about the sign of the dot product. So if you look at the dot product, right, at this geometric formula for the dot product, this magnitude part, it's always greater than or equal to 0, right? And it's only 0 if the vector v is 0. But the same is true for the magnitude of w. That's going to be greater than or equal to 0. So the only part of this product, magnitude v, magnitude w, and cosine theta, the only part that could make it be negative is this cosine part. And that's determined completely by the angle theta. So the sign of the dot product depends only on the angle theta. So let's think about what that sign tells us about the vectors v and w. Right, there are kind of three situations. So the first situation is if, not theta. I want this to say cosine theta. This should say cosine theta as well. So what happens if cosine theta is greater than 0? So what angles theta would make this, make cosine theta greater than or equal to 0, right? That's angles between 0 and pi over 2, not including pi over 2, right? So this cosine is positive when these two vectors, v and w, the angle between them is acute, right? So theta is acute here. In other words, v and w point mostly in the same direction. So that's when this dot product is going to be positive. So if v and w point mostly in the same direction, v dot w is greater than 0 because this cosine part is positive. Okay, what about if this cosine part is negative? Well, to make the cosine of an angle negative, that angle has to be between pi over 2 and pi, right? But the geometric situation then is that Right? V is pointing a long ways away from W. So in this situation, V and W are pointing mostly away from each other. And so in that case, V dot W is going to be negative, right? Because again, the sign of this cosine part is controlling the sign of the dot product. All right. And then I guess the last case, right? We looked at what happened if this cosine part is positive. We looked at what happens if it's negative. So finally, let's look at what happens if the cosine of our angle is 0. Well, theta has to be between 0 and pi, and the only angle between 0 and pi whose cosine is 0 is when theta is exactly pi over 2. So in this situation, the angle between V and W is exactly a right angle. Okay, so in this case, V and W are perpendicular. When we're talking about vectors, for some reason the word orthogonal gets used instead of perpendicular. It means the same thing. Orthogonal. That just means perpendicular. Okay, so so two vectors are perpendicular exactly when the cosine of the angle between them is 0, and that's exactly when this dot product is equal to 0, right? So the geometric formula for the dot product, it gives us it has all this geometric information packed inside of it, but just by looking at the sign of the dot product, you can tell if the vectors point mostly in the same direction, mostly in opposite directions, or if they're perfectly perpendicular to each other.